I mentioned back in topic 5.1 electric fields the concept of power, and we need to go back over that again now that we've got a better understanding of some of the concepts associated with current, voltage and resistance. And we're going to start off first of all by looking at that equation where we saw that P is equal to VI. What we're going to do now though is combine that with Ohm's law, V being equal to RI. We're going to do it in two different ways. So the first thing that we're going to do is substitute that equation for V into the power equation. So we can say that P is then going to be equal to RI, so there's the expression for V multiplied by I, or in other words, P is going to be equal to I squared R. So there's an alternative version of the power equation that relates the current and resistance together to calculate that power. Alternatively, we can use Ohm's law to identify that I is equal to V over R, and so we have a different form of the equation, so we can substitute in there that P is going to be equal to V multiplied by V over R, so that's going to then be equal to V squared on R. So the equation that's in the data book that combines all of those, we have that P is equal to VI, which is equal to I squared R, and it's also equal to V squared over R. So that's the equation that incorporates all of those aspects. In the end, they're all equal to power, but you can use whichever one you need to depending on the quantities that you're given. Now it might look like there's a bit of an unusual scenario here, in that it would seem that we have two proportional relationships that don't seem to work together. So one being that P is proportional to R, considering that P is equal to I squared R, and then also it seems that P could be proportional to 1 on R, since P is equal to V squared over R. So we have these two conflicting relationships, and in order to clarify it, what we need to consider is that we have other quantities that are involved here. So we're going to start first of all by looking at I being constant. So if I is constant, then we have that relationship that P is proportional to R from P equals I squared R, and we also have from Ohm's law that we're going to see that V is proportional to R as well. So when the current is constant, if you increase the resistance, you increase the potential difference. So if we then go across and consider V squared on R, V is going to increase, R is going to increase, but V increases with the square, and so we have this situation where V is not actually constant, and so we can say then that in that situation P is not proportional to 1 on R. I'm going to represent that by just putting a big red cross through it. So if I is constant, then P is proportional to R, given that with a constant current, increasing resistance increases the potential difference, and that's also then going to increase the power. The alternative then is if V is constant, and we're going to see very much the opposite. So we have then the proportional relationship will be that P is proportional to 1 on R, and again from Ohm's law we would see that the proportional relationship we're dealing with there is that I is proportional to 1 on R. So in this case, if we increase the resistance, that means that the current's going to decrease, considering that the voltage is constant. So increasing the resistance, the current decreases. So if we then consider P being equal to I squared R, with an increase in the resistance but a decrease in the current, which is squared, we're going to see a decrease in the power. So in that situation, increasing the resistance will cause a decrease in the power, so that proportional relationship P being proportional to R isn't valid in this scenario because the voltage is being kept constant. So which of those proportional relationship applies depends on which quantity is kept constant. If neither of them are constant, then we don't have any proportional relationships to consider, because a change in the resistance might change both the current and the voltage, and so the power is going to change accordingly. However, as I said, that was just to clarify any confusion that might exist in this equation with the fact that we have I squared r and then v squared over r. In the end, the important thing to note here is the equation that's highlighted there, that the power is the product of the potential difference in the current, or we can use the resistance, and if we know the current then it's I squared r, if we know the potential difference then it's v squared over r.